Welcome to my video tutorial on program codes. In this session we will look at chapter 3 OLG-1.g from chapter 3 of my book on public economics. In order to run the program you need a working version of Gauss. You should go to my homepage and download the code from chapter 3 and you should also download the teaching material from my book, which I provided for all chapters, so in particular the slides on chapter 3. So let us turn to the economic problem first before we go into the program code. On slide 24 of my teaching slides for chapter 3 you find the numerical example. It is a two-period overlapping generation model where the period length corresponds to 30 years. The population growth rate is set to 10%, which amounts to approximately 0.3% annually, and which is a value in close accordance with empirical evidence from the United States. Lifetime utility is additively separable in utility from consumption today and tomorrow. We choose a logarithmic function and the discount factor beta is set to 0.4, which amounts to an annual discount rate of approximately 3%. Production is Cobb-Douglas and capital K and labor L, and we set labor equal to the cohort size of the young generation, so each young agent in our economy supplies 1 unit of labor inelastically. As a consequence of the constant returns to scale production function, we can express wages and interest as a function of the capital intensity lowercase k only, and the capital intensity is defined as aggregate capital stock over population size n. We set production elasticity alpha equal to 0.36 so that the labor income share amounts to 64% in our model. We neglect any depreciation of capital in this simple model, and accordingly savings amount to those provided in equation 20 as a consequence of our logarithmic function for utility. The capital market equilibrium, in which aggregate capital stock is equal to aggregate savings, is provided by equation 21. So this is a dynamic function of kt. It provides kt plus 1 as a function of kt, so it's a first order nonlinear equation, and in steady state where capital stock is constant, our capital intensity k amounts to 0.06. This implies the steady state values of the wage rate W, the interest rate R, savings S, output Y, and consumption C1 and C2. Now the numerical problem that we would like to study is the dynamics of the capital stock if the initial capital stock K0 is not equal to the steady state value K, but in our case to 1/3 of the capital stock. And the dynamics look like the one displayed on slide 29. So the capital stock adjusts from 0.02 to the final value of the capital stock 0.06 relatively fast within 3 to 4 periods, and it converges smoothly. The dynamics display stability. Now let's get to the Gauss program. Start your Gauss version. In my case it's Gauss 19, and you will be presented with a screen that looks almost like this one. Might look a little different, but in essence it's the same. And we will start by loading our program from the directory where you have stored the computer programs of chapter 3. So we load chapter 3 olg91.g into Gauss. Next, make sure that the working directory is set equal to that where you stored the program. So the working directory is displayed in the upper menu bar, and if it's not the right directory, select the working directory with the help of this function here with clicking the 3 dots. Now the program chapter 3 olg91.g, I introduced a header which provides information on the name of the program, states the purpose, so it computes the dynamics of the example economy and about the author and the date. And I inserted it between 2 @signs, so Gauss will ignore all the text between the 2 @signs. In the first line, line 11, I start the program with a couple of commands: new, clear all, CLS for clear screen, that will help to clear the memory of your computer so that no former assignments of particular values to a variable will be used in this program. This might have very misleading effects on your results. If you do not know a particular command, you may use the help function and search for this command in the library provided by Gauss. And for example, the command new has the purpose to erase everything in memory, including the symbol table. Now let's go back to the edit mode. In line 12 we specify a library. This contains certain graphics commands provided by Gauss, so you can ignore it. And in line 13 we provide the machine accuracy to our source file derivatives.source src that you also stored in the same working directory. In this source file we saved a procedure derivatives which allows you to compute the Jacobian of a function. And the procedure must know the accuracy of your computer, which is stored in markups. In line 16 we initialize the variable plot style. In my case I use Gauss 19. This value must be 19. If you use an older version of Gauss, Gauss 18 or smaller, please insert 0 in line 16 and save it. And if you use Gauss 19, use plot style 1. So you save the file by clicking File and Save. A short key would be Ctrl+S. Now, in order to understand the logic and the commands in your Gauss program, it is helpful to first let it run by pressing the green arrow and see if it works. And as you can see, the dynamics are displayed and everything looks fine. I introduced a wait statement, so you have to press any key on your keyboard to continue. And in the second part, final part of the program, the derivative of our function g of kt is computed, so it's 0.36, meaning that it's stable. The absolute value is below 1. We have a stable, steady state. And of course, this is also shown by the convergence of our capital stock over time. Now switch back into the edit mode. And to understand the execution of the program, go into the debug mode. So the debug mode allows you to execute line by line, and your screen should look something like this with the bright yellow bar, which gives you the current line of the program that is executed. Use the 4 arrows in the top menu to move in debug mode. So if you press step over F9, you get to the next executable line. And let's go to line 18, where I parameterize the model with alpha equal to 0.36, beta equal to 0.4, and n equal to 0.1. In the debug mode, you may move the cursor on top of a variable, here it's alpha, and Gauss will provide you with the value of this parameter 0.36 that you assign to it. If you have not yet assigned a value to a variable, Gauss will inform you accordingly. So in line 24, we compute the steady state value, which is simply the equation provided to you on page 27 of the slides, and initialize the capital stock in period 0 with 1/3 of the steady state value. So our initial value is 0.02. In line 28, you initialize the time periods that you would like to display in your figure. So this TT is a column vector starting from 0 to 19, and KT is the vector, the column vector where you store the results for the capital stock K0 to K19. So the first entry in KT of 1 corresponds to K0 and so on. So in line 32, you initialize the first entry of this series on the capital stock, the vector with 0.02. Now in the following 5 lines, lines 33 to 37, we fill the entries of this column vector. So compute kt plus 1 with the help of kt using the function 21 in the slides. So in order to run this loop, let's go to line 35. We have initialized I with the value of 1. In the loop it will be increased by 1. So now the value of I is equal to 2. And we will compute the entry of kt of 2, which is our k1, with the help of equation 21, which is the right-hand side of this equation. So now we have computed the second entry in this column vector, which amounts to 0.041. And now we can just go through this iteration, but this is a little bit cumbersome, so the debugger allows you to jump to the next executable line by using this arrow, run to cursor here, press this menu point in your upper bar, and you run to line 40 and have computed the 20 entries of your capital stock. So we have used forward shooting, starting with the value of kt and computing kt plus 1 iteratively to compute the whole dynamics of the capital stock. Now, as I said before, plot style checks if you use Gauss 19 or an older version. We use Gauss 19, so we jump into the second part of the if condition in the else part and simply provide all the plotting commands that Gauss uses. So the labeling of the x-axis, the labeling of the y-axis, the title of the plot, and in line 53 we specify the x variable, which is equal to our time periods, and we specify the y variable as the capital stock vector. Next, the dynamics of the capital stock are displayed. We go back into our debug mode and we execute line 56, which is the wait statement. So now the command line waits for that you press any key. You can do this if this window is opened in the right hand side. If not, just go back to command mode, press any key on your keyboard, and you may now go back to debug because this line has been executed and we can move on. In line 58 the Jacobian is computed, if you want to find out how the computation is done, you may move the cursor into the procedure chi-dyn, where the right hand side of the equation 21 is provided. So this is the equation that we would like to evaluate the derivative with respect to k, t, which is our variable x in the procedure. So we move to the cursor. X is the variable 0.006, which is our steady state capital stock, and to move back into the procedure that called chi-dyn, this is our procedure that computes the Jacobian, and to move out of this procedure into the upper level of the command, just press step out F10 and you're back to the debugging mode of the main program part. And line 59, the Jacobian, the value of the Jacobian is simply stated. Now the syntax of our command cdjac is given by the procedure, so you have to give the name of the procedure of your function to Gauss, to cdjac, and if the argument is the function, you have to include an ampersand in front of the name kdyn. The value at which you would like to evaluate your Jacobian is the second argument of this command, and the third argument provides the dimension of the function. So in our case it's a one-dimensional function. We just provide the argument 1. And in the final line of the program, line 50, the Jacobian is printed on your screen. So if you go to your screen, you find 0.36. If you go back to debug, you just press the debug mode now is finished, as you can see. When you click the red square. So this concludes our tutorial on the program chapter 3 OLGDyn1.g. I hope you enjoyed it, and if you have any questions left, please do not hesitate to contact me, send me an email, and I try to answer your email as soon as possible.